A liter of air initially at room temperature and atmospheric pressure is heated at constant pressure until it doubles in volume, so it goes from V to 2V. Calculate the increase in its entropy during this process. Okay, I did this problem and I have recorded while I was doing it, but for some reason the recording did not go through. So I'll just go ahead and explain what I did. So here we are talking about a gas, air, and it's initially at room temperature, and this is the pressure here is remaining the same. Hence, we are working in a in CP instead of CV. However, the formula does remain the same. To find the entropy, I would have to integrate. I would have to integrate from T initial to T final, Cp over Ct dt from okay. Now the therefore, the only difference between this formula and the problem before this one that we did is, instead of using the heat capacity at constant volume, because the volume is actually doubling here, it's not staying the same, we use the heat capacity at constant pressure, where the pressure is remaining the same. Now the question becomes, how do I find Cp? So now the way I reasoned this out is we know that Cp is equal to half F times Nr, where F stands for the number of degrees of freedom. So for a gas, a gas at room temperature, we know that there are 2 degrees of freedom. We have translation and we have rotation. So that's overall. So I do have translational motion, and I have the x, the y, and the z direction for the translational kinetic energy. So that counts as 3 degrees of freedom. That's just for a monatomic ideal gas. Now for a diatomic ideal gas such as air, which is made up of oxygen and nitrogen, I have an additional, since it's diatomic and there's 2 molecules, I would have an additional rotation where each molecule can rotate about 2 different axes, and because the third axis, the rotation about the axis that runs down the length of the molecule, doesn't count for reasons that have to do with quantum mechanics, that we can discuss it in a different class. So that would add another 2 degrees of freedom from rotation. So this is translation rotation, and so that's a total of 5 degrees of freedom. And now comes, depending on the temperature, the diatomic molecule can actually vibrate. So if as if 2 atoms were held together by a spring, this vibration can also contribute an additional 2 degrees of freedom, right? Because you have if there's more complicated molecules where you could have flexing, twisting, etc., and each vibration counts as 2 degrees of freedom, but here we're talking about a diatomic gas. So the question is, do we have those extra 2 degrees of freedom coming from vibration? And I think in this problem, yes. And the reason, first, because the temperature will change as a result in the change of volume, as I show here. The temperature will double, so we will go from room temperature to double that. The second thing, when I went to the tables in the back of the book of Schroeder, he does use Cp of gas. He has a value that matches my 7/2 Nr, not my 5/2 Nr. So I do know that my total degrees of freedom has to actually be 7. So I use 7/2 F Nr, 7/2 Nr, and again, because when I calculate this, I get exactly what he has for air at the end of the in the tables. Okay, for both nitrogen and oxygen. These are the air molecules. Okay, so back to entropy. So then I would integrate from Ti to Tf Cp over dt. So this would be ln T evaluated from T final to T initial, so ln T final minus T initial. However, I don't know the ratio of temperatures. I know the ratio of the pressures, but I know that for an ideal gas law, since the pressure is remaining the same, the ratio between volume and temperature have to stay the same. So V final over T final has to equal V initial T initial. If you've ever taken basic chemistry, this is what they call I believe Charles' law. Okay, so that means the ratio between final temperature and initial temperature is the same as the ratio between final volume and initial volume, and since it doubles, this is just 2V over V, which is just 2, so I could replace 2 for the ratio of the temperature, TR over T initial, and I get 7/2 NR ln 2. Now here I do have I don't have basically what I did is I used the ideal gas law to replace NR with PV over T, and I know that this is the pressure is 1 times 10 to the 5th. I have the temperature is 300 Kelvin. This is room temperature, and I know that this is a liter of air, so I know that I started with 1 liter of air, I'm going to 2, so I changed that to meter cube, so multiplied by 10 to the minus 3, and then I got a positive increase of entropy as a result of this process to be 0.816 joules per Kelvin. Again, conforming to the second law of thermodynamics, where for spontaneous processes the entropy has to always increase. That's the essence of the second law of thermodynamics, and this result only testifies to that. That concludes the problem.